Welcome to this Quintus Technologies webinar regarding the high-pressure heat treatment of additively manufactured parts. My name is Jim Shipley. I'm the Global Business Development Manager for the Advanced Material Densification Division of Quintus, working with HIP and SIP equipment. The agenda today will be quite in-depth into different areas of our industry. But to start with, thank you for joining this webinar. And in the tool that you're currently looking at in the web, you can also post questions. So please go ahead and put some questions in there, and we'll try to answer as many as we can at the end of the webinar. We're going to cover the trends in the additive manufacturing market, a recap regarding high-pressure heat treatment, which you probably saw webinars of a couple of years ago, and the availability of modern HIP capacity in the market. We're also going to talk about the latest high-pressure heat treatment developments, and of course our Quintus application centers, where we're able to help you with the development of your own products. One of the most important parts of our business development at the moment is around steered cooling, the ability to actually tailor the cooling cycle in the HIP. And of course, this gives opportunities to be able to increase productivity in your additive manufacturing process. So to start with, trends in the additive manufacturing market. I think you're probably all aware of what's going on in the industry, but just to recap a little bit, lead time reduction has been a big driver. And prototyping to get new R&D products running quicker has been a major demand or an opportunity in the industry. And also replacing long lead time items where sometimes the deliveries are very, very long, up to 2 years. Digital warehousing has been moving ahead as well recently, being able to produce legacy parts that maybe you scan into your CAD file and then print. Also low turnover parts where it's very efficient to actually just produce them with additive manufacturing rather than ordering a minimum order batch from another production process. New production items as well and repeatable production are possible using a digital warehouse. Design freedom has been discussed for a long time, and new designs are possible, producing previously impossible parts. Also fewer components and weight savings, which has been a big driver, of course, for the aerospace and automotive industry. This is all leading to some pretty interesting demands on the industry, which is going to be addressed in this webinar. One of them is repeatability, the industrial robustness of the product, to be able to put this material into production and ensure that it's going to function as it's planned. Guaranteed properties from the products is also very, very important, so that every time you print it, you get the same material properties out of the production line. The availability of the products is also extremely important to be able to get the parts very quickly, but also from reliable sources. One of the other trends that's been running recently is larger parts. There's been a focus in the industry over the past few years on predominantly small parts, but that's changing. And when printing larger parts, the build times are extremely long. So quicker production is very, very interesting. And also there's an opportunity here to reduce the production time whilst having builds running for several days anyway, but producing very large parts. The AM value chain has also seen some major recent developments. The end users are wakening up now to the possibilities with additive manufacturing and driving then the need for applications and designs and also industry specifications around this area. The suppliers to the AM industry have been pushing this for many years. And here we have, of course, design software companies, powder manufacturers, wire manufacturers, and of course, suppliers of post-processing equipment such as ourselves. And in between here, there's a growing sector of additive manufacturing service bureaus who are basically filling the gap between the suppliers of the machinery and the end users who have the demands on the application and also the rights to say yes or no to business cases and give approval for service of the parts. So I'll just give a little bit of a recap now regarding high-pressure heat treatment based on some webinars that you may have seen previously. There was actually a series of webinars run in 2018 which are available on YouTube, so you can go in and look at those on our YouTube channel. 3 different webinars regarding high pressure heat treatment. But of course, some things have changed since then, so I'm going to touch on that today. So what is high pressure heat treatment, or HPHT as we call it? Many HIP designs have slow cooling rates. And this is a traditional way of just turning off the heaters and letting the machine cool down. Microstructure modification and optimization was done later on by heat treatment in further operations. Modern Quintus HIP systems can achieve high cooling rates. And this means that basically you can adjust the material properties and the metallurgy of the material in the one operation after HIP. So whilst the material is hot, you're just steering the cooling of the material to achieve the right mechanical properties and material properties. Conventional post-processing of AM parts has several steps, and in this case for laser, you can see stress relief of the parts is quite common, of course, and needed for most alloys. And then you have a HIP, usually, for high-end parts, and solution heat treatment, and then aging for some of the precipitation alloys, where we want to achieve a certain mechanical property later on. What we do at Quintus is actually combine these into one process. So we do this in the HIP, using the cooling and actually steering the cooling today to achieve the right material properties in one shot. This gives a lot of advantages actually, such as reduced number of process steps, cycle time and downtime, of course, but also improved quality control because you're not moving the parts between different parts of the chain. Less time at elevated temperature is also a big advantage here, so grain growth in material can be controlled in a better way. It also gives benefits, of course, around lead time and energy consumption and cost, and of course the total investment that you're putting into the parts. The capital investment can be also lower based on the fact that you need less machines. An example of high pressure heat treatment could be, as an example, not an AM product, but a single crystal turbine blade, where some work's been done at the University of Bochum in Germany, which is a really excellent work and good example of what can be achieved in terms of metallurgical development using the HIP. Here they've compared a normal heat treatment cycle for a high-end nickel alloy, a nickel-based superalloy, and also compared this then with high-pressure heat treatment using a Quintus HIP with a combined cycle. And the optimized material properties can be seen here by the fine microstructure in the lower end of the slide here. You can see that the initial porosity for the conventional production route is about 0.25%, with a nicely distributed gamma prime structure. However, with the high pressure heat treatment, we can pretty much eradicate the porosity completely and obtain a very, very fine microstructure. You can read more about this in the papers that the University of Bochum have already published. So, the availability of modern HIP capacity, and when we're talking about modern HIP capacity, we're meaning the ability to steer cooling and also cool material very quickly. There are 2 real areas where you can see things developing. One is the use of service providers, where many companies maybe don't have the volume or the desire to have their own HIP equipment, so they use service providers. And these can be very, very cost efficient when it comes to small production volumes, good availability, of course, because you have several suppliers to turn to. You can buy a ticket on the bus, if you like, in a coach cycle or a standard HIP cycle. And of course, the providers of the modern Quintus HIP equipment are able to offer the tailor-made HIP cycles, the high-pressure heat treatment cycles. No HIP know-how is really needed because you can go to the service provider and they offer that for you. And of course, you can avoid the capital investment of your own machine. But some other companies decide, yeah, we have enough volume or we have enough interest to have specific material properties that we want to invest in our own machine. And here you can see a lower overall cost compared to insourcing it from other people, and reduced lead time, of course, because you don't have to send the parts out for subcontract work, which means that you have full control over the scheduling and planning, etc. Of course, the short cycle times available with the high-pressure heat treatment equipment also means you can produce more parts per year or per week. And of course, full control over the process means that you have control over your own quality as well. Quintus partnership with these companies also ensures that they get all of the application support and help from us in all ways of developing the tailored cycles as well. Some examples here in the US of some heat treatment companies that have taken a step into offering service for high pressure heat treatment and hipping are these four companies as good examples. So you have Stack up on the west, and HTMX in Mexico, Accurate Brazing, and Paolo Heat Treat. And all of these companies offer HIP service as well as, of course, the heat treatment services, etc., that they normally would supply. This means that you have an availability in North America now, which is really, really, really good for this kind of technology in large vessels as well, which can give good capacity utilization. Also, some companies have decided to insource this. Some companies working with AM, as an example, Burloak up in Canada. You have Oerlikon and also Syntavia, who have taken big steps, all three of these companies, in terms of developing special cycles, but also offering the industry ready-made parts from their own production. So this is an interesting development for us as well, and they've invested in really modern equipment with this capability. Some of the machinery that's now available from Quintus can be seen on the screen now, and we have the QIH60, which is a small unit for additive manufacturing purposes, but also very useful for castings. And this is a 410 millimeter diameter cylinder, 1 meter high, which can be used for high pressure heat treatment of parts, and also it fits a 250 by 280 build plate. Here you can get cooling rates up to and above 500 C. 500 C per minute is what we're offering as a minimum, but depending on the load in the machine, it can be much higher also. These machines have already been sold and are available to the market. For larger parts and also for larger production volumes, we have the QIH 122, which is now available at a number of sites in North America. And here we have a 660 millimeter diameter vessel with a 1.75 meter height. This means you can get in a lot of parts in one of these machines, and due to the high pressure heat treatment and the short production cycle, you can actually use this machine for very quick production as well, giving good options. All of these machines come with the ability or the opportunity to buy a Quintus Care program from us. And this is a partnership program that we offer our customers to help them with any questions regarding the equipment, of course, but also application development, materials, accessibility, and how to use the machines in a good way. And companies buying a press from Quintus have the opportunity to sign up for this and have the opportunity to work with us on R&D projects, etc., and have access to our application development specialists. A lot of the application development is done in our own application centers, where we're offering R&D work for universities, for customers. If a customer has a production unit, they can do R&D work in our unit whilst using their own one for production. It means that we can do evaluation of the processes ourselves and develop our own machinery, of course, but we can also develop new processes for our customers. We also use this, of course, for training of companies that have bought machinery from us. And the aim is really to develop the knowledge around hot isostatic pressing, but also cold isostatic pressing and other processes. The R&D collaborations that we have with a number of major universities are also leading to a large number of papers coming out on the market now for high-pressure heat treatment. So I recommend that you go in and search on hot isostatic pressing in whatever media you use for getting access to these papers. The support services we have are basically testing in-house of the different HIP cycles. Also optimization of HIP cycles to try and improve material properties. And this is all manner of different products and grades of material. Training and education is done in this equipment to show how to use it and how to control the processes. And of course we look at load optimization, how to place the parts in the machines, but also how to optimize the gas flow, etc., to gain the correct material properties that you're looking for. We can also do small-scale production to do trials and pilot runs for customers. And of course we develop collaboration around marketing material with customers as well. The application centers that we have running at the moment are in both Sweden, where the main center is, but also in North America, in Ohio, in Columbus. And here we have a number of different machines available, both hot isostatic pressing and cold isostatic pressing, but also a warm isostatic press that can do a lot of lamination, etc. These application centers can actually model and be used to predict any of our products, regardless of size. So we have the capability to model based on the smaller units to see what would happen in a larger unit. Some examples of our own R&D work that have been going on now that might be useful to you in your own work. Steered cooling is probably the most important one. It's a revolution when it comes to heat treatment in HIPs. And there are a number of things that you need to know to be able to work with FEM and modeling of the flow rates, the material characteristics, etc. The gas temperature, of course, we know from the HIP, from the thermocouples. The thermal conductivity of the material, where we know, of course, from the data that's supplied with the material. And the specific heat, which is also a typical material attribute that we can find in literature. The thing that's difficult to work out is the heat transfer coefficient, which is between the gas and the object, the ability to transfer heat between the two. And this can be used to, if we had this, of course, to calculate the cooling power that's possible in the equipment based on the gas flow, etc. So cooling rate is basically dependent on gas flow in the equipment, if it's turbulent or laminar, the gas properties, the density, the viscosity, etc., and also the heat transfer coefficient, which can be calculated and also be checked with experimental work. So I'm going to show you some slides regarding what we've done on this. In this little model here, you can see the modeling of the cooling in the HIP based on a cylinder in this particular case. And we can do this for any kind of part, really. In this experiment, we actually had bars of different diameter and different lengths. And we've had a thermocouple inside the material in the core at the half of the radius and at three quarters of the radius. And check this at different pressures also to see what is the cooling rate that's actually achieved in the equipment. The simulated and measured temperature in specimens can be checked, of course, and in this case it's the diameter 60 and on the right the diameter 20 millimeter parts, and you can see that the curves have slightly different angles. This is at 500 bars. And in this case, we calculated the heat transfer coefficient, alpha, to be 3.75. And looking at 1,500 bars, things change. So we also saw that the alpha, the heat transfer coefficient, is much higher at the higher pressure. So this is an interesting learning from this work. But it means that we can actually predict what needs to be done in the HIP. But the heat transfer coefficient seems to be linear related to the pressure of the gas. If we look at the heat transfer coefficient in a HIP compared with conventional heat treatment methods, it's very similar to a 10 bar nitrogen quenching. It's very different, of course, than oil quenching, water quenching. But what you can say is that the controllability of this is extremely good compared with putting this in an oil bath or something. The pressure or the gas density influences the cooling rate in the material, because we know that the heat transfer coefficient changes with pressure. So in the finite element simulations, we can actually look at specific parts from CAD drawings that you can supply us and actually look at the real cooling in the part for you. And in these two plots, you can see the 1200 C plots from for 200 seconds at different pressures. So obviously the heat transfer coefficient of 550, you get the more heat transfer than you do at 375. So running at higher pressure has a benefit to heat transfer. It means you can also cool the parts quicker. So how can we use this? Here we've calculated the required gas temperature to achieve a 30 degrees C per minute cooling rate. The geometry of the component is needed, of course, for this. The material with the required data there, the technical data, but also the required cooling rate in the material based on the specifications you're using or your own demands. And then the output is the actual gas cooling rate that we need to ensure that the machine can do for you. Normal natural cooling of HIP equipment entails shutting off heaters, and the cooling time is dependent on the amount of cooling of the actual vessel itself. And this can be very, very long. It's not a very homogeneous cooling either. We can see that the thermocouples in different parts of the vessel give very different readings in this particular graph. So here you can see a 45-minute cooling from 1300 C to 400 C. And the ejectors are not used in this normal natural cooling to assist. Our own patented process, which is uniform rapid cooling, or URC, is a much shorter cooling time, and it takes only 8 minutes in this particular case from 1300 C. And good temperature homogeneity is seen in the furnace, throughout the furnace, because we're using either ejectors or a fan to drive the flow of the gas. And this gives us really rapid cooling, which is very, very useful for additive manufactured parts. We can steer the cooling by putting a thermocouple wherever you want, in a dummy part if you want, or in an actual part if there's a hole for the thermocouple. And based on this, the gas cooling rate, we can program the machine using this thermocouple to steer according to that cooling rate. And this is what a graph can look like when we're actually aiming at a 30 C per minute cooling rate, which is achieved then by varying the gas cooling rate, you can see to the left here. And this is very, very flexible now, and it means that you can actually steer the material cooling rate exactly how you want it based on the material itself, rather than the gas cooling rate or the thermocouple in the gas. This gives great opportunities in terms of optimized cooling results and repeatable products, material properties. And of course, for a large number of alloys in the industry, everything from castings, of course, to AM, can be heat treated in this way using HIP to remove the defects in the products and then tailor the microstructure of the material based on a desired cooling rate. And of course, the material can be cooled very, very quickly in these modern units, which means that you can basically achieve whatever you want to do with different materials. The steered cooling enables parameters to be programmed, which then can be repeated time after time after time, giving the industrial robustness needed for the process. And steering of cooling based on a thermocouple or a dummy part has been proven and can be done in this equipment. And of course, the specific heat treatment cycles can be developed then for improving product quality and different tailored microstructures based on this. So if you want to try this, you just have to contact us and we'll help you do some trials and show you what can be done in this area. So here's a case study for titanium 6.4 material in an AM production line setup, which is really quite an interesting area for many industries. We can see that the HIP and heat treatment part of the whole process is actually quite a small cost in the total part of the supply chain. So in order to get the costs down for parts, we need to focus on the parts away from the HIP and heat treatment area, the ones that take a long time. And this basically means that you've got an opportunity to reduce, of course, your powder costs or your pre-material costs, your wire costs, but also the machine setup time, the printing time, and then also the post-processing steps after the heat treatment. This is an area where I think that can be enormous steps in the coming years to actually reduce the total cost of additively manufactured parts for the industry. In this particular case, University of Hamburg, Technical University of Hamburg, and Dr. Dirk Herzog have done some work looking at, okay, what happens if we print quicker? What kind of density do we get in the different in this material, titanium 6.4, with varying hatch distance and also energy input into the additive manufactured build. And a lot of work's been done on this, and they've identified some areas now where down to 95% density can be achieved, but with very a bigger process window, if you like, for production of the parts. And these are some of micrographs presented last year at the MRS spring meeting. And you can see here on the left is the normal way of producing with as dense as possible material. And this, of course, after HIP is still very dense and good material. But by increasing the speed of the laser speed by 67%, the density drops to around about 97.75. And after HIP, it's completely closed again. The same goes for 171% or 71% higher speed, laser speed. And here you can see that the density drops off a little bit to around 94%. And it can also be closed with HIP. So this gives you an enormous opportunity to increase the laser speed or the hatch spacing or the layer thickness of the material. So to play with producing parts with porosity in order to then subsequently HIP them, heat treatment them in the HIP, and improve the material properties. So the sweet spot, if you like, the ability to have a look at a bigger process window is actually proven already and can be used to increase the speed on the parts. In this particular case, we've combined this work with some work by a Paderborn University and a PhD student, Dominic Ahlers, who's also presented work regarding what can be done with the tailored HIP cycles. So in this particular case, where Dirk Herzog's taken the Airbus fuel connector part, he's achieved a reduction of time, obviously the build time for the part, by 26%, and also, of course, the density is not great after printing, but can be fixed in the HIP. And using the tailored cycles that Dominic has been working with us on, we've been able to get up the strength of the parts to the same level as the as-built material, but with extremely improved elongation results. So the tailored 1 and tailored 2 cycles here give extremely good results with higher strength and also improved elongation, at the same time as removing defects using the HIP process. So what does this mean for the industry? Well, in this particular case, the fuel connector is normally 14 components, so 50% of that can be reduced just by printing it. A further improvement of the build time by 26% means you can save 7 hours in the build time, reducing the risk of the optics getting dirty, etc., and reducing the risk in the build. And then high pressure heat treatment can be implemented with these special heat treatment cycles to give an extremely good material performance, but printed with porosity from the beginning. So this is a very, very interesting area where the industry can see things happening. We can speed things up, and we can also get very, very good material properties. But there's always a question that comes, okay, what happens with the argon when you print on purpose with some porosity? Well, we've done some work on this as well. So here's some recent results that haven't been published yet, but I think this is the first time we show these now. But we printed 4 cubes, one with the normal solid printed parameters. In this case, it's Inconel 718. And we've also then printed with artificial pores to trap some argon on purpose. And then looked at this with normal heat treatment, with HIP and then heat treatment externally, and then HIP with high pressure heat treatment inside the HIP. And from the graph on the right here, you can see that the fully dense printed material has a little bit less argon in it, but we can also see that the argon does not diffuse out of the product with any of the other processes. So we know the amount of argon there based on the pores that we printed on purpose. We then took this a step further and made the tensile bars out of this for analyzing the fatigue properties. And so there was a spiral or a helix printed with 0.5 millimeter pores. And we ensured that they were at least 0.25 millimeters from the finished polished surface for the test bars. And these were then tensile fatigue tested with R 0.1. And what we can see here is that the Series 2, which is the printed material with the heat treatment and the pores, fractured at much lower level, has a lower fatigue resistance than the other parts. But what we could see is, and interestingly, the material that was printed with very large pores, actually, in this case, achieved extremely good fatigue resistance after the high-pressure heat treatment or the HIP and heat treatment cycles. But, of course, with the improved elongation results, which we already showed in the other slides. So what does this mean for the industry? Well, increased machine utilization and production economy is obviously very interesting. Shorter production times means you can get more parts out per day. And quicker printing of the large parts means that you don't have to spend so much machine time and also can reduce the risk in the build. And you can, of course, speed up the production for slow additively manufactured parts. When I say slow, I mean alloys that you have to print slower because of quality issues. One of the major benefits is really the material properties, the repeatability of this, where you can see that the spread in the results can be reduced. We can get optimized material properties the same every time, with improved elongation, excellent fatigue strength, and of course more equiax microstructures based on the HIP process itself. The quality assurance aspects that come from this are, of course, clear. And industrial robustness is a key area here, where the reduced need for inspection, the risk-free production environment, and also single-site production of parts, where by not sending parts out for subcontract processes is a major opportunity. This actually enables the factory of the future development for the additive manufacturing industry, with the ability to print difficult materials with less energy input, prevent cracking, and also introduce new tailored high-pressure heat treatment cycles for the development of the alloys. Of course, this can lead to development of own intellectual property as well in-house for customers using this. Thank you very much for listening. This is the end of the webinar, but we're going to move into the live question and answer session now to review the questions you've put online. But remember, you can find a lot more information from us and the latest technology developments on our website. Thank you for listening.